Let's talk about problem solving and number patterns. Now think about how you solve a problem. You probably have an approach to solving a problem, or maybe several approaches. And that's exactly what George Polya thought about when he wrote his book, How to Solve It. He thought about how we should approach solving mathematical problems. And he decided that there was really a four-step problem-solving process that we could use to solve any mathematical problem. The first step is understanding the problem you're solving. Then you can devise a plan, and that means you can think about how you want to solve the problem. Maybe you're going to look for a pattern or look for some related problem. Maybe find a simpler case or make a table or a list. Drawing a picture or writing an equation or guess and check, working backward, or using direct or indirect reasoning. All of those are methods for solving problems that Polya said could be used for mathematical problems. Now after you devise a plan, he said you should carry out the plan. And most people think that's the end of solving a math problem. Once you've got an answer, then you're done with the problem. But Polya said there's one more step. He said you need to look back. You need to think about whether your answer makes sense, or whether you even answered the question that you were asked. Maybe there's a different way to find the solution, maybe an easier way, or maybe a more interesting way. So we're going to look at Polya's problem-solving process a little bit, and we're going to look at different ways to solve the same mathematical problem. But I'd like you to think about how you solve math problems, because as an adult, there's a pretty good chance that when you think of solving a math problem, this is what you think about. You think about algebra. And algebra is a wonderful method for solving problems, but let's face it, if you're going to be maybe an elementary school teacher, maybe a fourth grade teacher, well, those won't be the kids you're going to teach. These would be the kids you're teaching. So if you're a fourth grade teacher, you can't be teaching these kids algebra, although you might be teaching them algebraic thinking. So we're going to look at a few problems that can be solved with algebra or could be solved with some of those other methods that Polya suggested. Here's the first problem we're going to look at. A pen at the zoo holds giraffes and ostriches. Altogether, there are 30 eyes and 44 feet on the animals. How many of each type of animal are there? Well, let's think about how you might solve this problem. Coming from your algebra background, using that adult brain of yours. You'd probably say, well, I need to define some variables, so maybe I'll let x be the number of giraffes and y be the number of ostriches. And let's see, I'll have to have an equation that relates the eyes on the animals. So there's 2 eyes on each giraffe and 2 eyes on each ostrich and 30 eyes in all. So 2x plus 2y is 30. And then we have to think about the feet. There's 4 feet on each giraffe, and there's 2 feet on each ostrich, and there's 44 feet in all. So 4x plus 2y is 44. So now that we've got a system of equations, we might solve that system by substitution or elimination in this case. So maybe we'll multiply the first equation by 2 on both sides, and maybe multiply the second equation by -1 on both sides. And if we add the 2 equations, we can eliminate the x, we can solve for the y, and then we can use the value for y to solve for x. So y is 8, that means there's 8 ostriches, and x is 7, so there's 7 giraffes. Well, that's a wonderful way to solve this equation algebraically. But let's rethink this whole problem. What would we do if we presented this problem to a second grader? How could a second grader solve this same problem? Well, they'd have to go through some of the same thinking, but maybe they could draw some pictures to represent what was going on. So they might be able to say, well, every animal has 2 eyes, and there's 30 animals. Well, no, there's 30 eyes, so that means 2 eyes per animal. That's 15 animals in all. So let's start drawing some animals. That's an animal, and it has 2 eyes. Let's draw another animal. Let's see, that's 4 eyes in all. That's 6 eyes. Let's just do some skip counting here. 8 eyes, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30 eyes. Okay, there's 30 eyes on our 15 animals. Now we need to put some feet on the animals. We know that maybe they're all ostriches, so let's put 2 feet on each one. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28. That's 30 feet, but we need to use 44 feet. So let's see. We still need to put 14 more feet on these animals, and we can't just put 1 more foot on an animal because there aren't any 3-footed animals here. So let's put 2 more feet on as many animals as we can. So that's 32, 34, 36, 38, 40, 42, 44 feet. So let's see. Everything that has 4 feet is a giraffe, and there's 7 of them, and everything that has 2 feet is an ostrich, so there's 8 ostriches. So without doing algebra, but really by doing some algebraic thinking, we've got 7 giraffes and 8 ostriches. Now I'd like to show you how 7th graders did this problem. And some of these 7th graders were successful and some of them weren't. Here's kind of a guess and check method that a 7th grader was trying, and you can see they were maybe dividing by 2, maybe thinking there's 2 feet on a giraffe or an ostrich, or maybe they were thinking there's 2 eyes on an animal. They came up with 15 giraffes and 22 ostriches. Not the right answer, but you can kind of see what's going on inside their mind. Here's what another 7th grader did. Also perhaps kind of a guess and check, but actually making a table. And they did come up with the correct answer, 7 giraffes and 8 ostriches. And here is another example of guess and check, and in this case this is successful. Now it's a good time to talk about guess and check, which is a valid problem-solving method, but in order for it to be valid, we have to see at least one guess that was incorrect, and we have to see a guess that was correct. So that's what we have in this case. Several guesses that were incorrect, but we finally have the correct guess, and we've got the correct answer. 7 giraffes, 8 ostriches. So let's look at another problem. We want to find the sum of the numbers 1 plus 2 plus 3 plus, and then we continue the pattern, plus 48 plus 49 plus 50. Here's how a 7th grader did that problem. They just started to add the numbers, which I guess could work. It would take a while. Their sum looks like it was 595, which is not correct. So something went wrong in this process. So let's look at another way that this problem could be done. And this way is so important and so special, it has its own name. It's called Gauss's method. It's named after Friedrich Gauss, who is credited with coming up with this method when he was a child. So what Gauss said was, well, I've got all these numbers to add. Maybe I can find a pattern in the numbers if I just group them a little bit. So he decided to group the first number and the last number together. So 1 plus 50 is 51. And then if you group the 2 and the 49 together, 2 plus 49 is also 51. And group the 3 and the 48, 3 plus 48 is also 51. So we can pair these numbers up and get pairs that add to 51. Now the only question is, how many of these pairs do we have? If we know how many numbers we have, we can figure that out. So if we're adding all the numbers from 1 to 50, that's 50 numbers. If we're pairing them, 50 divided by 2 is 25. So there are 25 pairs of numbers, each of which add up to 51. So the sum of all the numbers is the number of pairs times the sum of each pair, which is 25 times 51, or 1,275. Now this is an important method to know, and you will have to know this and be able to demonstrate that you know this method. Here's how a 7th grader tried to do this problem. they were adding up groups of numbers as well. Kind of an interesting method. They added up all the numbers that ended in the same digit, and they actually found kind of an interesting pattern in those subtotals. And they added up all those subtotals and came up with the right answer. And here's how another 7th grader tried to do this problem. They were pairing up numbers as well. Interestingly, they decided that 50 was a nice number. So there was the number 50, and then when they paired up the 1 and the 49, that added up to 50, and the 2 and the 48, that added up to 50. So they had a lot of 50s that they were adding. In fact, they had 25 50s, plus, if you look in the middle of all these numbers, there's a 25 that couldn't get paired with anything at that point, so they had to add that 25 in the end, and they got 1,275, which is the correct answer. Here's another problem. If 10 people are in a room, how many handshakes can they exchange? Now, to solve this problem, we're going to use several of the methods that Polya said that we could use to solve problems. First of all, we're going to make a table where we compare the number of people in the room to the number of handshakes. 10 people in a room is a lot of people, so we're going to start with a simpler case, which is thinking about what happens with one person. And we're even going to draw some pictures to represent the people in the room and the handshakes. So we're just going to have a single person. Now that single dot is a single person, and one person can't really shake their own hand, so if there's one person in the room, that's no handshakes. If we add a second person in the room, they can shake hands once. If we add a third person, they can shake hands 3 times. If we add a fourth person, they can shake hands 6 times. Now we could continue this and keep drawing pictures, but as you can see, the pictures might get a little complex. So let's see if we can find a pattern in the table, and we're going to look for a pattern in the handshakes. So if we go from 0 handshakes to 1 handshake, that means we've added 1 more handshake. If we go from 1 handshake to 3 handshakes, we've added 2 handshakes. From 3 to 6, we've added 3 handshakes. Now we do have a pattern here. We've got 1 plus 2 plus 3. So if we have 5 people, that means we have to add 4 more handshakes. And 6 plus 4 is 10. 6 people, we'd be adding 5 more handshakes. 10 plus 5 is 15. 7 people, we'd add 6 more handshakes. 15 plus 6 is 21. 8 people, we'd add 7 more handshakes. 21 plus 7 is 28. 9 people, add 8 more handshakes. 28 plus 8 is 36. And finally, 10 people, add 9 more handshakes. 36 plus 9 is 45, so there are 45 handshakes. So we have a lot of different ways to look at this problem. With our table, we're looking for some patterns. We've got some pictures. We started with simpler cases. Now if you look at those numbers, 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8 plus 9, it's kind of interesting to see that this is exactly what a 7th grader noticed when he was trying to find the answer to this problem, and he did come up with the correct solution. This student didn't quite come up with the correct solution. They decided that there were 90 handshakes. The mistake they had in their reasoning was they weren't realizing that if 2 people shake hands, that's only 1 handshake. So if I shake your hand and you shake my hand, we're really only exchanging 1 handshake. So they're double counting the handshakes. That's why their solution is twice as big as it should be. This student did come up with the correct solution, but they also said that maybe there's infinity handshakes. if you can shake a hand more than once. And this one, although it's wrong, is got to be the most interesting one. It's a good example of what happens when a student doesn't really understand what the problem means. This student decided that each person has 2 hands, and that means they have 10 fingers, so there must be 200 handshakes. I think they did 2 times 10 is 20, and then 20 times 10 is 200. It's not correct, but it's certainly interesting and a good example of how important it is to understand the problem before you try to solve it. Here's the next problem. Mark and Bob began reading the same novel on the same day. Mark reads 6 pages a day and Bob reads 5 pages a day. If Mark is on page 78, what page is Bob on? So let's think about Mark. So Mark's on page 78, and we know that he can read 6 pages every day. So that means he's been reading for 13 days. Bob's been reading for the same number of days, and he can read 5 pages a day. So Bob has read 5 pages a day for 13 days, and that means he's on page 65. Here's how a 7th grader did the problem. Basically the same reasoning. Here's how another 7th grader did the problem. A really interesting way to do it. They made a table and they looked for a pattern in the table, comparing the number of pages for Mark and Bob, and they came up with the correct solution. And this student also made a kind of a table and was looking for a pattern, but they found an even more interesting pattern. They were looking at the differences between the number of pages Mark has read and the number of pages Bob has read. So you never know what students are going to come up with. They're going to see all kinds of things that you maybe never thought of. So here's another problem. If a bag of potato chips and a Snickers bar together cost $3 and the chips cost $1.50 more than the candy bar, how much does each item cost separately? So here's what a 7th grader did to try to solve the problem. They did not get the right answer, and this is pretty typical for a wrong answer to this problem. They knew that the 2 together should cost $3, and they knew the chips cost $1.50 more, so they used that $1.50 and that $3 in an interesting but incorrect way and decided that they had to cost the same amount, which certainly can't be true if the chips cost more than the candy bar. So let's think about a way we could approach this problem. We could use a guess and check and compare the cost of the chips to the cost of the candy, and keep in mind that guess and check has to show at least one incorrect guess and the correct guess. So let's start with that student's incorrect guess, which was the chips cost $1.50 and the candy cost $1.50. Well, the problem with that is that the chips and the candy cost the same amount. We've spent $3, but the price difference in the 2 isn't what it should be. We should have a difference of $1.50. So we know the chips should cost more, so let's make the chips cost more. And we know we still have to add up to $3, so we've got a total of $3, but at this point the chips cost $2 more, and they're supposed to only be $1.50 more. So we'll make the chips a little less expensive, and we'll make sure that the 2 items can still add up to $3. And at this point, the chips cost $1.50 more, so we found our solution, which is the chips cost $2.25 and the candy costs 75 cents. Here's a student's work on this problem, and this would be with guess and check, and you can see the incorrect guess and the correct guess, so that would get full credit. One last problem. Billy spent 2/3 of his money on baseball cards and 1/6 of his money on a candy bar. And after that, he still had 50 cents left in his pocket. How much money did he start with? So we're going to look at this problem as a picture. And the picture we're going to draw is a box that represents all the money that Billy went to the store with. So we've got his whole box of money. Now what's important here is the box represents the whole here, and we're going to look at some fractional parts of that whole. Now we know he spent 2/3 of his money on baseball cards, so we'll divide the whole up into 3 equal parts, and we'll show that 2 of those 3 equal parts he spent on the baseball cards. Now the remainder of the money was spent on a candy bar and something left over. So we're going to have to divide the box up into 6 equal parts because we know that he spent 1/6 of all the money on a candy bar. So now we can say that this 1/6 of the whole was what he spent on the candy bar, and the remainder of the box was the 50 cents he had left over. Now since we've got 6 equal parts to the box at this point, we know that each of the 6 equal parts represents 50 cents. So now we can see that we have 6 parts, each of which are 50 cents, and 6 times 50 cents is $3. So he started with $3. Here's how a 7th grader did this problem. They did some work with fractions. They said 2/3 plus 1/6 is 5/6, and the remaining 1/6 was the 50 cents. So then they multiplied the 50 cents times 6 to get $3. Basically, they've done the same work we just did, but they just worked with the fractions. They don't have the picture. Here's another student's work, basically saying the same thing. 5/6 of the money was spent. 50 cents times 6 is $3. So basically they've got the same thing. And then we have a student who made an attempt at adding the 2/3 and the 1/6, got the 5/6, and then lost sight of what that really meant, that was 5/6 of the whole. Ended up with an answer of 8/6, and then realized something was dreadfully wrong, and basically gave up and said, "What?" So that's a look at some different types of word problems. There's lots more different problems than that, but we've looked at lots of different methods for solving those problems. So you're going to get a chance to solve some word problems with different approaches. Remember, there are lots of valid approaches. You just have to be brave enough to try them.